Okay, so this is very cool. I'm going to show you a really satisfying identity here with sine and cosine, where if you take the sum sine 0 plus sine 1 and so on up to sine of some integer, divide that by the same sum with cos in place of sine, then we'll get a really satisfying result. So we'll start off just looking at this with n equals 5, and then we will be able to generalise this. We'll do the general proof once we've just seen the idea of the proof with n equals 5. So the very first thing I'm going to do is just reorder the sum. So this is just like how Gauss did with his sum of integers from 1 to 100. I split them up into pairs. And you'll notice in each pair you've got 3 plus 2 is 5, 4 plus 1 is 5, 5 plus 0 is 5. We'll do the same thing with cos. So cos 5 plus cos 0. This is going to be useful because we're going to use the sum to product identities for sine and cos. So I'll write out what they are just in a sec. Okay, so first of all, your sum to product identity for sine, if you've got the sum of sine of two different numbers, sine of a plus sine b, this is always equal to 2 sine of a plus b over 2 multiplied by cos a minus b over 2. So this is our sum to product formula for sine. And you can derive this using your angle addition formula here and here for sine and cos. It's not too difficult to work out, and then tidy up, and you show this is equal to sine a plus sine b. And then there's a similar formula for cos a plus cos b, which is basically the same thing, but you've got a cos in place of that sine. So you've got 2 cos a plus b over 2 multiplied by cos a minus b over 2. And this is really nice, and it's very useful for what we're doing here, because you see here sine of a plus b over 2, cos of a plus b over 2, all of these will just be 5 over 2, because the sum of each of these pairs is 5. So let's write out the next step then. So sine 5 plus sine of 0, you get 2 sine of 5 over 2, and then multiplied by cos 5 minus 0 over 2. And then we've got another 2 sine 5 over 2. So this is nice, these are all going to factorise. Cos of 4 minus 1 over 2. And then also we get 2 sine 5 over 2. Cos 3 minus 2 over 2. And we'll get a similar expression in the denominator. Now we get 2 cos 5 over 2. Cos 5 minus 0 over 2. You see there's some of the same structure here, plus 2 cos 5 over 2, cos 4 minus 1 over 2. So this looks very promising. We're getting the cos 4 minus 1 over 2 repeating as well. That's 2 cos 5 over 2, cos 3 over 2 minus 2. Oh, this is very nice. You can see when we factorise, we're going to get some things which cancel. So let's do that. So this is 2 sine 5 over 2 multiplied by, so this becomes cos 5 over 2 plus cos 3 over 2 plus cos a half in our numerator. And then what do we get in our denominator? We get something very similar, 2 cos 5 over 2 multiplied by the exact same sum, cos 5 over 2 plus cos 3 over 2 plus cos 1/2. This is really nice because you can see here your 2's cancel, and then actually this entire sum here cancels as well. So we get sine 5 over 2 divided by cos 5 over 2 which is just tan 5 over 2. And there's another 2 ways you could write this as well, using what you call your half-angle formulas. So if you have tan of x over 2, basically I'm going to write this as sine of 5 divided by 1 plus cos of 5. And then you can also write this as equal to 1 minus cos of 5 divided by sine of 5 using your half-angle formulas. So for 2 other very satisfying ways writing this. So I'll have a go at generalising this in a sec. Just to say with the half-angle formulas, basically what you can do is you can derive this half-angle formula, tan of x over 2 is sine divided by 1 plus cos, basically from the angle sum to product formulas. So you can do sine of 5 is the same as sine of 5 plus sine of 0. This is the same as cos of 0 plus cos of 5. So you can set a equals n, or a equals 5, and then b equals 0. You can derive this one. It's not too difficult from your sum to product formulas. And then to get the second one here, you just multiply the top and bottom by 1 minus cos 5 and use the fact that sine squared plus cos squared is always equivalent to 1. So for the general proof, I'm going to split up into two cases where n is odd and where n is even. I just think it's easier to follow this way. So first of all, we write it with sigma notation like this, the sum from 0 to n of sine k. And now, when I reorder the sum, you can convince yourself that this is actually the same as summing from j equals 0 to now up to n minus 1 over 2, where we're doing sine n minus j plus sine of j. So here you start off when j is 0, you've got sine n plus sine of 0, and so on, and then you meet in the middle, but n minus 1 over 2 is an integer when n is odd. And then we divide this just by the exact same expression with cos. Then we're going to use the sum to product formula here, just with the general n's and j's. So now we apply the sum to product formula, and what we'll find is this is equal to just the same sum again. So here we've got n minus j plus j, so it'll be 2 sine n minus j plus j all over 2, multiplied by cos n minus j over 2. We can tidy this up in a sec. We'll just write out the next step as well. We do the same thing for cos, so you've got the sum up to n minus 1 over 2 of, now it's 2 cos n minus j plus j divided by 2, multiplied by cos n minus j over 2. It's just using the sum to product formulas again. And here this is nice, you can see in this fraction your 2's will cancel first of all, then also you've got n minus j plus j, minus j plus j, so these give you your sine n over 2 and cos n over 2. And these don't depend on j, so we'll take those out of the sum now. So what I can do is rewrite this as sine n over 2 into the sum from j equals 0 to n minus 1 over 2 of just cos n minus 2j over 2. Now this is all divided by cos n over 2. We can take that outside of the bracket again, that doesn't depend on j, multiplied by the same sum as in the numerator. So n minus 1 over 2, again it's cos n minus 2j over 2. And we don't care what this sum actually is, we know it's not going to be equal to 0, so you can just divide through by each of these, and then you're left with just sine n over 2 over cos n over 2, which is of course tan n over 2, which is what we were trying to prove. So now we've done this where n is odd. Finally, if n is even, it's a very similar argument to before. It's just when we try and split them up into pairs, you end up with one left over. So basically we write this out very similar to before, sum from j equals 0, but now we go up to n over 2 minus 1, which is a whole number because n is even. Then we're just writing sine of n minus j plus sine of j. So again, we're starting with sine of 0 plus sine of n. We almost get to the middle, we have n over 2 minus 1, and we have n over 2 plus 1 here, but then we've also got this leftover sine of n over 2 term, which doesn't form a pair. Put this in brackets. And then we get the exact same thing in the denominator, and we'll apply the sum to product formula. So once again, start with cos 0 and cos n, and then we have this one left over in the middle, cos of n over 2, which doesn't form a pair. So what we do next is, I'm going to skip the step, some of the step where we apply the sum to product formula. I'm going to take out this factor of 2 sine n over 2, that we had just before, and then this is still multiplied by the sum from j equals 0 to n over 2 minus 1 of, now we've got cos n minus 2j all over 2. And then we've still got this leftover sine n over 2 term. And hopefully you can see this is we'll be able to factorise this in a sec. And then you do the same thing in the denominator, you get 2 cos n over 2, which you can take out of the sum because it doesn't depend on j. And you're left with the exact same sum, cos m minus 2j all over 2. And we've got this leftover cos n over 2 term, just as before. So now the 2's don't quite cancel, but we can take out the factor of sine n over 2 and cos n over 2. So that leaves us with sine n over 2, which is being multiplied now by 2 times by the sum to n over 2 minus 1 from 0 of cos n minus 2j over 2. So we've got 2 times this sum plus 1. And then in the denominator, you get the same thing, but with cos n over 2. We have 2 times by the sum. And then we've still got a 1 left over as well from this cos n over 2 term when we factorised. So this is really nice because now you can see this entire bracket will cancel in the numerator and denominator. And then you're left with sine n over 2 divided by cos n over 2, which is tan n over 2, which is what we were trying to prove. So we've done this for n odd, and we've proven this for n even, so we're done here. And just to say as well, there's another way you could approach this problem where you can use the fact that sine of k, this is the same as the imaginary part of e to the ki. You could use the fact that cos k, this is the real part of e to the ki. And then you can express these sums as partial sums of a geometric series and have a go at this using complex numbers if you like. Personally, I find this approach is probably the most straightforward though.